My hair grows longer and longer as we are trapped here. So today is finally my first response to Papa Flammy in a long time. And this is sort of a little stopgap until I get to the real generalization bomb that's coming soon. Probably next week. Or I'll wait till he responds to this one. It depends. Maybe he has a small little gem to respond to this little gem, this little ruby I've got going on. So today we're going to be exploring integrals of powers of the cosine function. Now that may seem mundane, and that may seem, elementary, sophomoric even. Well, as we all know, the integral of cosine over a certain interval, and we know the recursion formula for cosine, but I'm going to expand beyond that and address what is the complete closed form expression for the integral of a certain set of powers of the cosine function. And so that's the generalization, but there is a neat fact that comes out at the end that I didn't know, and I don't know that it's obvious to prove just looking at it, or if it's already been known, I simply don't know the answer to that question. So let's just get into it, shall we? Let's do some math. Alrighty, got my trusty cup of joe here, of course. He was steaming before, it was getting very hot in here. Anyway, so let's talk about this. So, where are we starting? We all know, having taken some calculus maybe, if you're privy to such information, that if we take the definite integral of the cosine function, we're all pretty aware that if you take the derivative of sine, you get cosine. So if you do the definite integral, you need to know the antiderivative of cosine, which sort of has to be the sine of t, and we're evaluating this from 0 to x, which naturally gives us sine of x minus sine of 0, but sine of 0 is 0, so you're left with the function sine of x. And it's not too hard to see how we would, evaluate cosine cubed if we worked it out and we sort of, used Pythagorean identities and figured it out just by using what we know about calculus and trigonometric identities. And it wouldn't be that hard, but I don't really feel like going through and doing every integral of every power because that would take forever. But we should maybe consider what this function will look like as, say, we consider this number. So let's say the integral from 0 to x of cosine of t to the power of 2k plus 1. Now, that may seem odd that I'm only picking the odd powers, but you'll see that it sort of works out in the end. The even powers sort of have their own thing, and I'm sort of just going to focus on this today. This is our generalization in a certain sense. We're going to find a nice, finite, closed form for the integral from 0 to x of cosine of t to the power of 2k plus 1 dt. And we will call this ck of x, which makes this c0 of x, right? Because 2 times 0 is 0, plus 1 is 1, and that's what that function is right there. So, how might you want to start off? Well, first of all, we want to see if we can maybe write it as a product of two things and do integration by parts, and it's not too hard to see how we would easily start that off, so we'll write it as the integral from 0 to x of cosine of t squared, or I'm sorry, to the power of 2k times cosine of t dt, right? I simply took one of the cosines and separated it out, and now we can use integration by parts, right? So we'll differentiate that, and we'll integrate that. So we have cosine of t to the power of 2k. Differentiating brings the power down and lowers the power by 1. And then we have to multiply by the derivative of the inner function, which is negative sine of t, so I'll bring the negative out the front and put the sine of t right there. And then, of course, we have a dt. And now we have to integrate cosine of t dt, and that gives us sine of t, of course. And now we simply multiply those two together and subtract the integral of those two, and we end up with sine of t times cosine of t to the power of 2k from 0 to x, and now we're subtracting the integral of these two terms. So we're going to get minus, so those are going to cancel, and we're going to get plus 2k times the integral from 0 to x of cosine of t to the power of 2k minus 1 times sine squared. And what we can do now is sort of evaluate this part right here. If we plug in x, we just get sine of x times cosine of x to the power of 2k. And if we plug in 0, all the cosines will be 1, but the sine will be 0, so that will go away. So the 0 term doesn't actually matter. And so we end up with just sine of x times the cosine of x to the power of 2k. And now we have here plus 2k. So we can break this up into 1 minus cosine squared, distribute this onto those, and break that up into two different integrals. Well, it's just cosine of t to the power of 2k minus 1. And that will be the first integral. And then we're subtracting 2k times the integral from 0 to x of cosine of t to the power of 2k minus 1 times cosine squared of t. Because remember, sine squared of t is 1 minus cosine squared. So cosine of t to the power of 2k minus 1 times cosine squared will increase the power by 2, so we get cosine of t to the power of 2k plus 1 dt. Notice, this is our general integral. And this is our general integral at k minus 1, because this is 2k minus 1 as opposed to 2k plus 1. Which means we can rewrite this in terms of the function title c sub k of x. So we know now that c sub k of x is equal to sine of x times cosine of t to the power of 2k plus 2k times c sub k minus 1 of x minus 2k times c sub k of x. But we want c sub k explicitly, right? So what we can do is add this c sub k term over, and then we'll have 1 plus 2k times c sub k. And then we will simply divide both sides by 2k plus 1 so as to solve for ck. So what I'm doing is I'm adding this term over to the other side, right? And we get c sub k of x times 1 plus 2k, right? And then we're just dividing that over to the other side, thus resulting in the final, or not final, the reduction formula for the integral of powers of cosine, which is that ck of x is this whole formula right here. So what I'm going to do, before I divide both sides by 2k plus 1, is I'm going to factor out sine of x from both of these things. So what that's going to do is it's going to cause there to be sine of x out the front, and in parentheses we have cosine of t to the power of 2k, and then we're adding 2k times ck minus 1 of x, right? Because you're plugging in k minus 1 into the general integral formula. But remember, we're factoring out sine of x, but notice there is no sine of x factor here. So when we factor it out, we actually have to divide by the sine of x. And that may seem a little confusing, but you'll see why. It's sort of a way of developing this recursion formula. And now, remember, we have the product of ck and 1 plus 2k on this side, so I'm just going to divide both sides by 2k plus 1. And now that sort of keeps that as a factor on the outside. But now we have a recursion formula, right? It might not be exactly the one that I flashed up on the screen before, but it will be equivalent, right? What we're saying is the integral from 0 to x, the cosine of t to the power of 2k plus 1, is equal to sine of x divided by 2k plus 1 times the quantity cosine of x, my mistake, to the power of 2k plus 2k over sine of x times the integral from 0 to x of cosine of t to the power of 2k minus 1, right? Because we're plugging in, we're essentially saying one integral can be put in terms of a lower power. And essentially we're just going to keep doing that again and again and getting lower and lower powers, and we're just going to end up with a sum of things that's going to be equal to the original integral. So I'm going to erase all the work we just did and move this back up to the top. So we were able to develop this recursion formula, and we're simply just going to do this again and again to get a sort of closed form expression for the integral of any odd power of the cosine of x. And so all we have to do is simply apply this rule to this right here, because this is just another version of this, but lower down. And so we simply have to apply the rule to this again and again and again, and that will eventually get us the general form. So let's see, we can probably deduce the pattern quite quickly. So this sine of x over 2k plus 1 will stay right here, and this cosine of x to the power of 2k will stay right there. But now let's apply the rules. Let's see what happens. So we need to replace ck minus 1 with sort of this thing for k minus 1. So what are we going to get? We're going to get 2k over sine of x, and now we need to sort of put an entire thing inside of this. And then it will all simplify, and we'll be able to sort of see what it is that we have to do from now on. So we need to replace it with sine of x over the next one down, so 2k minus 1, times the quantity cosine of x to the power of 2k minus 2 plus 2k minus 2 over sine of x times c of k minus 2x. So this equals ck minus 1 of x, right? We just replaced this with all this, using the recursion formula that we just derived, right? So we're simply nesting recursions within each other. But we can see that things will nicely simplify in a way, because I apologize, this should just be like this should be written like this, sorry. So cosine of x to the power of 2k minus 1 plus 2k over sine of x times ck minus 2, this should be, sorry, plus 2k minus 2 over sine of x times ck minus 2 of x. And now that should all be parenthetical, right? And then we're close brackets, and then big brackets again. So these are the brackets that go with each other, these brackets go with each other, and these brackets go with each other. Okay? So now we can simply distribute and simplify. All the signs are a little confusing looking, but you'll see that they sort of just reciprocate each other and cancel. So we have our cosine of x to the power of 2k. Now let's see what occurs. So these two signs are going to cancel, right? And that's good. These two signs are going to cancel, and we're left with this one in the reciprocal like we were before, right? And still only with the first one out the front, right? Like we had right here, which is what we have here. And now we have 2k divided by 2k minus 1 times the cosine of x to the power of 2k minus 2 plus 2k minus 2 over sine of x times c sub k minus 2 of x. So we've sort of applied the recursion formula to this term, got this part, and then simplified, and we see we've sort of been left with two of these cosine power terms, whereas we had one before. And if you keep this pattern going and you continue to work it out, you will see that this just ends up being... Oh, I made an error. I apologize. So, because of these two factors, 2k and 2k minus 1, they should also be here in this fraction. My bad. So this should be slightly bigger. This should be 2k times 2k minus 2 divided by 2k minus 1 times sine of x times c of k minus 2 of x. And so this sign in this denominator is going to be continually canceled by the sign that we get out of using the recursion formula. And in the end, there won't be any of them except this one right here. That was sort of the point of factoring them all out. Because what we're going to end up with is this, sine of x over 2k plus 1 times the quantity cosine of x to the 2k plus 2k over 2k minus 1 times cosine of x to the 2k minus 2 plus 2k times 2k minus 2 all over 2k minus 1 times 2k minus 3 times the cosine of x to the power of 2k minus 4 plus dot 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 all the way down. And what you might notice is that these numerators and denominators are sort of like a weird pseudo-factorial, right? Because what you'll end up with as you do these more and more is in the numerator you're going to get 2k times 2k minus 2 times 2k minus 4 times 2k minus 6 all the way down to 0 when we're finally, or I'm sorry, all the way down to 2 when we finally get to the last term, the constant term, right? The cosine to the 0 term. And that means that at the cosine to the 0 term, the entire numerator is going to be a product of all even numbers from 2k down to 2. And that's something that we call double factorial. Double factorial, x factorial factorial, is not x factorial and then factorial that number. Double factorial is sort of a skipping mechanism. So if we say 2 times n factorial, this is 2n times 2n minus 2 times 2n minus 4 times dot 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 all the way down to 4 times 2, right? So it's the product of all the even numbers from 2n down to 2, and if we did 2n minus 1 factorial, we would get 2n minus 1 times 2n minus 3 times 2n minus 5 times 5 times 3 times 1, right? And we go all the way down to all through the odd numbers. And we can actually deduce a way of putting these double factorials in terms of regular factorials, because you'll notice that not everything appears, right? In the constant term at the end, it will be entirely 2k double factorial divided by 2k minus 1 double factorial, right? And it goes all the way down to the constant term. And this term right here will be the one that has cosine to the power 0. And so it goes up by factors of 2, right? So, or at least it's going up by 2 every time, right? So 2k minus 4 plus 2 is 2k minus 2 plus 2 is 2k minus 0, right? And so we can actually generalize this relationship in this way. So this is plus 1, sorry. And we have a sum of things, right? And we're going to start at j equals 0 and go all the way up to k. Well, let's figure this out. Let's see what this is. So let's start at the bottom term, right? We know that it's cosine to the 0, and we're going to have every even power of cosine from 0 to 2k. So we want to start at cosine of x to the power of 2j. Because when j is 0, we'll get our constant term. When j is 1, we'll get cosine squared. When j is 2, we'll get cosine to the 4th. And when j is k, finally, we'll get cosine to the 2k. Right? Pretty easy. So we're sort of building the even powers right into the sum. But now we need to figure out what are these coefficients of all the powers of cosine. Well, at the bottom, at the very bottom, right, with the cosine to the 0 term, we have 2k double factorial over 2k minus 1 double factorial. So I know that those things sort of have to be there. But the funny thing is as the powers get bigger and bigger and bigger, right, we're just sort of chopping off the last factor of the numerator and the last factor of the denominator every single time we go up, which is to say that as j increases, we're cutting off the bottom parts. But we can say that we're like dividing out the bottom parts of these things. So you may notice that we can just write 2j minus 1 double factorial divided by 2k minus 1 double factorial, right? So this is sort of a way of chopping off these as j goes up, right? Because when j is 0, I'm sorry, this should have been, I apologize, this should have been 2j double factorial in the denominator there. Because notice, at 0 double factorial is sort of by definition 1. We can actually explore this a little bit. So if we consider, let's use this area right over here to explore this idea a little further, right? So 2k factorial, double factorial, is a product of all the even numbers from 2k down to 2. That means there are k numbers and they're all being multiplied by 2. So we can rewrite this as 2 to the power of k times k factorial. Because think about it, this is the product of every number from 1 to k. If we then have k factors of 2, we can multiply each of those numbers by 2, and then we get 2k double factorial. Because this is all the numbers from 1 to k multiplied by 2 and then multiplied by each other. So this sort of accounts for all that. We can do the same with the odd double factorials by simply looking at 2k minus 1 double factorial, which is the product of all the odd numbers from 2k minus 1 down to 1. But what we can do is write this as 2k factorial divided by 2 to the k times k factorial. Now, why might that be the case? Because what we can do is consider what the bottom is. Well, the bottom is just 2k double factorial, right? 2k double factorial is 2 to the k times k factorial, which is what we have in the bottom. But remember, that's a product of all the even numbers from 2 up to 2k. And that means since we have 2k factorial, that's a product of all the numbers from 1 to 2k. So if we only divide by the even ones, we must end up with a product of all just the odd numbers, which is why this is the same as 2k minus 1 double factorial. And so we can replace these things with this stuff and get a better idea of what this series is, because we don't want to put it in terms of double factorial. It's not as intuitive or obvious to us. So what we want to do, I hope that was clear as to how we got these answers, right? So this was easy to derive. Maybe think about it a little more and it'll become clear, but those are the ways you can write the double factorials in terms of single factorials. So what we're going to do is we're going to remove everything that doesn't depend on j from the sum, because I want to sort of focus just on the sum. So what we're going to do is we're going to factor out these k double factorials out to the front, and you'll notice we have a little bit of a simplification, right? We have sine of x, and then we had 2k double factorial, but we also had that factor of 2k plus 1 in the denominator. And I think it's kind of clear, if you multiply 2k plus 1 times 2k minus 1 double factorial, you end up with 2k plus 1 double factorial. Because 2k plus 1 is the next odd number after 2k minus 1. So multiplying them together gives you the next double factorial. So we don't need those in there anymore. So this is what we're left with. And this is our general, the integral from 0 to x of cosine of t to the power of 2k plus 1 dt. So this is our general form, and this is the generalization of the video that we wanted to see. So we have a little bit more work to do, but this is interesting. This is very, very cool stuff. So we were able to derive, by using repeated applications of the reduction formula for the powers of cosine, for the integrals of powers of cosine, to come upon this, right? So we have a closed form. This is a closed form expression because it is a finite sum. K is a finite number, so this must be a finite sum. So this is, by definition, a closed form expression for this antiderivative right here, which is very, very neat. So this is what we just proved, right? This relationship right here. And so what we're going to do is we're now going to explore what this general function, ck of x, might actually look like. So of course we know what the cosine function looks like. Because we're taking the area under a curve that's oscillating, this function, this area, as x gets bigger and bigger, is going to oscillate up and down, like this function does. So what we're going to do is we're really going to consider x's between 0 and pi. 0 and pi. And so, of course, starting at 0, x equals 0, the area is 0. And then it increases, increases, increases until we get to here, at which point it starts to go down, right? Because now the area is negative. And as we raise cosine to bigger and bigger powers, right, since it peaks at 1 and goes down to -1, the absolute value of most of its points is less than 1. So the powers of it are going to get smaller and smaller and smaller. And the reason I pick only odd powers of cosine is because that means that this stuff will stay negative and this stuff will stay positive. So that's sort of the reason, and it creates this. No matter which power we pick, it sort of creates this image. So it starts at 0 and then it rises to some maximum and then it goes back down to 0. And the reason I drew it like that is because as the power increases more and more, the integral over that will get flatter and flatter and flatter. And because the area beneath the curve of higher and higher powers of cosine gets smaller and smaller, it must be the case that ck of x goes to 0 as k goes to infinity, because the cosine function gets squished, right? The places where it equals 1 stays the same, but as we raise k really, really high, it starts to look something like that. The function starts to look kind of wonky, right? Obviously this part is gone now, but it starts to get very, it has to stay at 1 and -1 there, but then it shoots down really quick to 0 as you raise k to bigger and bigger powers. So this area gets smaller and smaller, which means this little hump that gets created by applying this this integral gets smaller and smaller because the total area underneath higher powers gets smaller. Here's what we're going to do now. Let's find out, because this is between 0 and pi. And of course when we get to pi, the total area under the entire curve gets to 0, right? Because we started with all this positive stuff and then we subtracted the exact same amount away. So it has to go from 0, reach some peak, and then go back to 0 at pi, right? And that peak has to be dead in the middle at pi over 2. So we can find out exactly what ck of pi over 2 is, right? And that's what we're going to do right now. We're going to figure out what is the height of this function right in the middle. So let's plug in pi over 2 in for x. So we get ck of pi over 2, and this is actually pretty brilliant because sine of pi over 2 is 1, and cosine of pi over 2 is 0 for every power of cosine except the 0th power, because what's the 0th power of anything? It's 1. So at the point 1, at j equals 0, this is 1, and this is 1. And sorry. Let's talk real quick about double factorials again, real quick, right? Because 5 double factorial is 5 times 3 times 1, right? And 3 double factorial is 3 times 1. And 1 double factorial must therefore be 1. So essentially we're dividing by the previous largest term, which means by that logic that -1 double factorial must be 1 divided by 1, which is again 1. Does that make sense? I hope that's clear. And you can keep going with all negative integers negative odd integers. You can't actually do the same for even ones because you eventually have to divide by 0. So, but let's just take a look at what we get. So we get 4 factorial equals 4 times 2, and then, or maybe you don't. 2 factorial equals 2 double factorial, sorry, which means 0 double factorial has to be 2 divided by 2, which is 1. But the only one we need to consider is the fact that negative 1 double factorial is also 1. And that 0 double factorial is 1, because when we take a look at plugging in j equals 0 into this, we get cosine to the 0, which is 1, and then we get negative 1 double factorial, which we just deduced was 1, and we get 0 double factorial, which we also just deduced was 1. At every other power of cosine, plugging in pi over 2 is going to be 0, so we only get the term where j equals 0. So what we end up with is 2k double factorial divided by 2k plus 1 double factorial times sine of pi over 2. For j equals 1 up to k, every term will be 0, because cosine of pi over 2 is 0. But at the j equals 0 term, it's 1. So this is the final result, but the sine of pi over 2 is also 1, and so this is the size of this function right in the middle. So ck of pi over 2, the maximum of any of these powers, of integrals of powers, is got to be 2k double factorial over 2k plus 1 double factorial. So what that means, what we're going to do is, because even though this function goes to 0 as k goes to infinity, as can be seen by the fact that this term is bigger than this term, right? Because we're multiplying bigger numbers than we're multiplying on top. If I divide this quantity over to the other side, then that in effect normalizes the integral, because I'm dividing by the thing that it is at the peak, which means it brings the peak of the function up to 1 and keeps it there. So let's make sure we're all clear on as to what I mean here. So this is essentially what some integral will look like, right? So this is supposed to be more or less flat, and then it goes back down to 0. So this is 0, this is pi, and this function is ck of x, right? And this point here is pi over 2, because that's what we plugged in, comma 2k double factorial over 2k plus 1 double factorial, right? That's that point right there, because we're plugging in pi over 2, and that's the number that we get. So what we're going to do is we're going to divide this function by this number, which will in effect cause the entire wave, no matter how big, or the entire function, no matter how big k is, will force this point to go up to 1. Right? Now this point will always be pi over 2 comma 1 if we divide this amount from this side of the equation to the other side of the equation, because we're forcing the largest part of it that will go to 0 eventually to always be stuck at 1, which will cause this function to sort of wrap up and sort of push up against the sides eventually, actually coming out to be a square wave in the end. We know that if I multiply this term over, this will force the middle of it to always be equal to 1. So we're actually going to do that. We're going to multiply this part over to the other side. What this has done, right, we've normalized ck of x, because we've multiplied by the biggest part, the reciprocal of the largest part, which also goes to 0, so that it's stuck at 1. But let's assume that we didn't know that it goes to 0. Let's say we wanted to prove that. How would we prove that? Well, we know that it sort of clearly has to decrease over time, because the area underneath it is getting smaller and smaller. So we know that at least the maximum of this integral has to be getting smaller. We don't necessarily know that it's got to be 0 per se, but let's see if we can show that it has to be. Or let's see what a consequence of that would have to be. Now that we've done all the generalization work and we've done some cool math, we're going to deduce a very cool fact now. So we had something that's going to 0 everywhere, because its maximum is clearly going to 0, times this normalizing factor, which sort of forces the maximum to always be 1, which, since everything's going to 0, doing this will force everything to eventually go to 1 under this function, which means that as k goes to infinity, what does that mean that this has to be? That means that this term right here, this infinite sum, has to be the reciprocal of this, because their product will have to go to 1 as this curve wraps closer and closer to the line y equals 1. So it essentially looks like this for some very large k. It looks pretty flat, and here's y equals 1. And essentially, as k gets bigger and bigger and bigger, it looks more and more like this, right? And it slowly just wraps closer and closer and closer, and you eventually, in the limit, end up with a square wave as k goes to infinity. But the only way we can know that is if this product is 1 in the limit as k goes to infinity. So let's consider that. That would mean that this series, as k goes to infinity, would have to be equal to the cosecant of x for all x, or at least the absolute value. So let's see if we can prove that. So this is the claim. My claim is that the sum from j equals 0 to infinity of the cosine of x, power of 2j, times 2j minus 1 double factorial over 2j double factorial is equal to the cosecant of x, the absolute value of the cosecant of x for all x not equal to an integer multiple of pi. So k in the integers. That's the claim, that this is equal to the absolute value of cosecant of x for all x that's not equal to pi times k, where k is an integer, right? Because then we'd be dividing by 0. So let's see if we can prove this. Well, let's call this I of x. Let's plug in the arc cosine of x in for x, which is going to cause this term to just be x. So we have that I of the inverse cosine of x is equal to the sum from j equals 0 to infinity of 2j minus 1 double factorial over 2j double factorial times x to the power of 2j, right? Because I've plugged the inverse cosine into here, which is going to cancel with the cosine and just give us x. And now what we're going to do is we're going to integrate. We're integrating from 0 to t, which isn't that hard to do because none of these things depend on t. Sorry, that should have been x. None of these things depend on x, and we're just going to be left with this power, x to the 2j, under the integral, which we know how to easily integrate because that's just the reverse power rule. So we just end up with the sum from j equals 0 to infinity of 2j minus 1 double factorial over 2j double factorial times the integral of 2 to the x to the 2j, which is x to the 2j plus 1 over 2j plus 1. Integrated from 0 to t, but of course plugging in t into this, we just get t, and plugging in 0, we get 0. And this may be familiar to some people who have taken Calc 1 or Calc 2. This is actually the inverse sine of t. This is the arc sine, and I'll pop up the Wikipedia article for this. Boom, there you go. Feel free to prove this to yourself. It's a lovely little fact. But what does that allow us to do? That allows us to take the derivative of both sides, and we will know exactly what this I of inverse cosine of x is. So if we take the derivative with respect to t on both sides, we will end up with the fact that the derivative of sine inverse of t, which turns out to be 1 over the square root of 1 minus t squared, if you remember that from Calc 2, it's not too hard to figure out, is equal to this I of inverse cosine of t. But all we have to do now is plug cosine of t back into this, right? Because we just want this to be x in here, right? Because we want to know what I of x is, right? This sum-looking thing that we derived. And if we plug in cosine of t into both of these things, we end up with I of x, right? I of t, right? Because arc cosine of t and regular cosine of t cancel each other. And we get 1 over the square root of 1 minus cosine squared of t. But what's 1 minus cosine squared? It's sine squared. So we get 1 over the square root of sine squared of t. But what's the square root of sine squared? It's sine, so we get 1 over sine of t, which is precisely the result that I claimed it would be. More or less. I said absolute value, but the absolute value just has to do with keeping it the same inside the branch between 0 to pi, because there are other branches of the function. But the point is, this sum, this series, this wacky-looking thing, is in fact the cosecant of t. What I'm saying is that the cosecant of x is in fact equal to this funky sum, this infinite sum, that you can plug into Desmos and see that it actually works. It's very, very strange looking. In fact, we can make it look a little less weird by simply replacing these double factorials with what we know them to be equal to for single factorials, right? We just derived those results from before. So what were they? So we have the sum from j equals 0 to infinity of the cosine of x to the power of 2j. And what was 2j double factorial equal to? That was 2 to the j
times j factorial. And what was 2j minus 1 double factorial equal to? That was equal to 2j factorial divided by the same thing. So again, 2 to the j times j factorial. But now we can sort of rearrange this again. We have 2 to the j times 2 to the j. That's equal to 2 to the 2j, and that's the same power as that. So we can rewrite this as cosine of x over 2, all to the power of 2 to the j. And now we're left with 2j factorial over j factorial times j factorial. But this also looks sort of familiar. This is actually the binomial coefficient, right? Because we have 2j factorial over j factorial times 2j minus j factorial, which again is just j. So if you're familiar with binomial coefficients, this thing turns out to just simplify in this way. So we have the sum from j equals 0 to infinity of 2j choose j. So if you had 2j objects, this is how many ways you can pick j of them out of all the objects. And so this might be the most elegant expression for the cosecant of x that I've honestly ever seen, because when we write it out, what we end up with, and so this is just an absolutely lovely representation of the cosecant function, or 1 over the sine, that is both an infinite sum and in terms of powers of the cosine of all things. So the generalization was this lovely expression that we have for the integral of any power, any odd power of the cosine of x, of the cosine of t from 0 to x, right? And this was the resulting fact that we were able to derive about the cosecant function, that it must be equal to this very strange infinite sum, which can also be beautifully expressed in this way. So I hope this was entertaining for you all. Papa, I hope this was a worthy generalization, though it was the video is long and there's a lot of symbols and it's detailed, but the actual fact is not a very special fact. We can quite easily derive this by simply reapplying a reduction formula. And so that's not that special. These two formulae are really sort of the special gems of this video. In the next generalization attack on you, Papa, I'm going to finally bring out the big guns. And it's going to have to be a two-parter. So stay tuned for that, and I await your response eagerly. Enjoy the pandemic. Thank you for watching.